Today, we will study about Newton's universal law of gravitation. Now, you all have heard about this famous story that there was an apple falling from the tree, and Newton observed apple falling from the tree, and that very act of observing the apple falling from the tree to the ground was sufficient for him to discover the law of gravitation. So, was it so instantaneous, or is there a still deeper story to it? So, let us see. Now, in simple terms, the story goes like this: apple falls to the ground, and Newton realizes that things are pulled to the ground. So, there must be a force acting on this apple towards the ground, and that force is the gravitational force. And in some sense, people think that itself is the discovery of gravitation. Well, that is not true, or it is not very accurate. Things falling to the ground is a common experience. Fruits fall from the tree, we drop objects, and those objects fall to the ground. And this is not a new phenomena what people had seen. People had seen this for thousands of years. In fact, many great scientists and philosophers had even attempted to understand these falling bodies, and they had studied it with fascination. So, let us see what other people had to say before Newton about things falling to the ground. Long before Newton, there was this Greek philosopher Aristotle, and he had made a statement. He had given a hypothesis, and not just hypothesis, it was also in a way a practical experience. What is that? He said that if you take a heavier object, and if you take a lighter object, and if you drop them from the same height with respect to the ground, if you drop these objects, then heavier object is going to fall faster and the lighter object is going to follow, and it is going to touch the ground slightly later. Now, this is something which we can consider as a common experience, because we all know that if I take a feather and if I take a heavier stone, then the stone would directly fall to the ground at a faster rate, and this feather would slowly fall to the ground. So, that being the reason, people did not refute this idea for a very long time. So, Aristotle had firmly believed that heavier object is going to fall to the ground faster and lighter object is going to fall later, slower. Now, if I translate this Aristotle's idea in today's language, okay, how would that sound like? It means Aristotle in some way thought that there is a force acting due to the ground on these objects, and that force acts in such a way that it acts more on this object perhaps and less on this object, more on a heavier object and less on a lighter object. So, this is going to be pulled faster and this is going to be pulled slightly slower at a slower rate. Perhaps a weaker, stronger force is acting on this object and a weaker force is acting on this object, and practical experience says that this is going to fall faster and this is going to fall slower. Now, was he wrong? Well, not completely. But was he right? Absolutely not. Then what? Common experience says that heavier object falls to the ground faster and lighter object falls slower. But why is he still wrong, and who proved that he was wrong? So, let us see. Long after Aristotle, there was this Italian scientist Galileo, and he can be considered as, in a way, a father of modern physics. Why? Because, as I said, Aristotle was a philosopher, and during his times, principles or hypotheses were given as thought experiments. You just imagine, you don't have to just go and prove it experimentally. But Galileo showed that you have to do experiments and then understand nature. So, Galileo was also fascinated by falling bodies, dropped bodies. When you drop two objects, how they fall to the ground. Galileo also wanted to study it, and he designed wonderful experiments using inclined planes to study the falling bodies. And all those experiments I'm not going to discuss here, but the conclusion he gave is, through his experiments, he proved that heavier body as well as a lighter body, they both fall to the ground at the same time if you drop from the same height. And this is true. And any deviation that you see, perhaps if you take a feather and a stone, if you see that stone falls to the ground first, it is because of the air resistance which is there here. If you remove the air resistance from the region, then a heavier body as well as a lighter body, both of them should fall to the ground at the exact same rate. And Galileo knew it, and he also proved it experimentally, and this was an established fact during Galileo's times. Now, he just did not say that both of them fall at the same rate. In fact, his experiments and research went even deeper, and he also said, and he also proved that both these objects, heavier as well as lighter, irrespective of whichever object you take, all these objects are going to accelerate when they fall down. That means what? It's not that both of them fall at the same rate or both of them travel with the constant same speed. In fact, both these objects travel with the same acceleration. And even if I take a third body here, even if I take a fourth body of different shape and size, all of them, irrespective of their mass, all of them are going to fall to the ground with the same acceleration. And that acceleration, he measured it to be approximately 9.8 meters per second square, which is we now call as acceleration due to gravity. Now, if I translate Galileo's ideas in perhaps today's physics language, I would say, then did Galileo think same force acts on both the objects? Well, not true. Then what is it? Then how come both these objects, heavier one and a smaller one, have the same acceleration when they fall to the ground? So, this is another interesting question. How does this force act on this object? If Earth is exerting force on this object, heavier object, as well as a lighter object, then how much is the force? Is it more on a heavier object and less on a lighter object, or vice versa? Or is it same? And is that the reason why both of them are falling with the same acceleration? So, to answer all this comes Newton. And Newton does some wonderful things with previous ideas, and he understands all these experiments by Galileo and all other hypotheses by other predecessors, and he comes up with a fantastic idea and a brilliant thought experiment. So what exactly is that? We will go to that. Okay, Isaac Newton, as you all know, is the brilliant scientist we have ever witnessed. So, before he came and tackled his falling body problems, he had already done a lot of things in physics. He had discovered the laws of motion, and we all know his famous second law of motion, which can be simply written as F is equal to ma. If a force is acting on a body of mass m, then it produces an acceleration a, and force, mass and acceleration are related to each other like this. And this is the famous Newton's second law, or in a way I can write second law as F is equal to ma under certain conditions. Now, let us come back to this. Apple falls to the ground, and when it falls, Galileo already told us that it accelerates with an acceleration which is around 9.8 meter per second square. A heavier object and a lighter object, both of them fall to the ground at the same rate, and both of them have the same acceleration, which is again around 9.8 meter per second square. So Newton thought, okay, so if Galileo has proven that both these objects have the same acceleration, and if I assume that both of them are attracted to the earth, or if earth is pulling both these objects with a force, then what does this law say? Both objects are having the same acceleration, and definitely we can make out that earth is exerting force on both the objects, which is gravitational force, of course. So this gravitational force which is acting on both these objects is slightly different, as we can make out from this equation, because you see both of them have the same acceleration, and this is having a larger mass, let me call it m1, and this is having a smaller mass, let me call it as m2. So what does this equation tell us then? If both have same acceleration, acceleration here is same as acceleration here, then definitely force must be different. Since both of them have the same acceleration, a heavier mass object should experience a higher force, a lighter mass object should experience a smaller force. In fact, force acting on these objects due to the earth, which we know as gravitational force, that should be proportional to the mass of the object. So this mass has a major role to play in this force, and Earth's gravitational force exerts slightly higher force on a body having a higher mass and slightly lesser force on a body having a slightly lesser mass. So Newton asked another important question, and that is the reason why we attribute the law of gravitation to Newton. And he asked some brilliant path breaking questions which perhaps no one had asked before. And not just asking questions, he himself found out the answers. So what exactly is that? Apple falls to the ground because earth exerts force on the apple. As we saw earlier, heavier objects fall to the ground, lighter objects fall to the ground. That means all the objects near the surface of the earth, they are attracted by the earth by the gravitational force, and they all tend to fall to the ground given a chance. Now Newton said there is an object which we see in the sky, moon. There are plenty of objects which we see in the sky, even during the night sky. But let us consider moon right now. Why moon is not falling to the ground? The question may look very funny, but that was an interesting question for Newton. Why? If earth can attract this apple, and if it can make the apple fall to the ground because of force acting on it, if earth can exert a force on a heavier object and make it fall to the ground when you are closer to the earth's surface, what about moon? Can earth exert force on the moon, or is it exerting force on the moon? If yes, why moon is not falling to the earth? If earth is not exerting force on the moon, then does it mean that gravitational force is only for earth and objects which are on the surface of the earth, and heavenly bodies or objects in the sky are exempt from this force? Is that so? Newton wanted to find out and investigate this, and he wanted to get an answer, so he decided to work on this. So he came up with a very interesting idea, and that led to the universal law of gravitation. So here is the interesting part. Let us get into it. So Newton also came up with a thought experiment, just like Aristotle came up with it. But Newton's thought experiment is not merely a simple thought experiment. It can be even proved experimentally. But anyway, let us see what exactly is this thought experiment. I'll tell it in today's terms so that you can relate with it. If you stand on a top of a building And if you have, let us say, a football in your hand, and you simply drop it from a certain height, you know it is just going to fall like any object, just like an apple falls from a tree. It is just going to fall down with an acceleration perhaps of 9.8 meter per second square. Now, instead, if you kick this football horizontally, right? If you kick this football horizontally, we all know from experience that it is not going to go straight forever. Why? Because Earth is exerting force vertically downwards, correct? Newton's first law would have said that if there is no force acting on this object, then this should have gone in a straight line forever. But we know practically what happens. You give a slightly horizontal velocity. Let us write velocity as u in physics as we do. If you give a horizontal velocity, you know that this is going to fall down ultimately to the ground, but not exactly below the point where you dropped it. Instead, it is going to cover a range, and the path taken by the object would be like this, and this is what we call as the trajectory, or simply path taken by the object, a half projectile we call it. Now, let us take this one step ahead. Newton said, what would happen if I had increased this initial speed? Very clearly, I can imagine that. I don't even have to do this practically. I can very well imagine that if I kick this with a higher speed, then this would fall here instead of falling here. So simply this projectile length would have increased, or in other words, the range would have increased, right? Now, what if I go one step further? What if I throw it with slightly even higher speed? You know that it is going to fall here. This object would have fallen here. What if I keep on doing this? You don't have to do it practically, remember. You have to just imagine, what if you were capable of giving an initial speed which is higher and higher and higher? Well, our common sense says that this range is going to become more and more and more, right? Because even if you give a very strong, very high speed, there is no way you can escape the gravitational force. You cannot go straight forever. You will ultimately, or that object will ultimately fall to the ground. But more initial speed you give, the farther it falls from the foot of the building. That is true. Now, what if I can give an initial speed in such a way that this distance will be, say, hundreds of kilometers and not just few meters? That is, you should give an initial speed so high that the distance covered should be hundreds of kilometers. Can that happen? Yes, of course. In my mind, I can always imagine that, because if I go on increasing the speed slowly, and if the range goes on increasing slowly, then if I increase the speed to a substantially high amount, this range should go for several hundred kilometers. If that is the case, then this picture will not be enough for me to further investigate or see what could happen. We have to look at the larger picture. Why? Because several hundred kilometers, if I write down here, definitely it is not going to be flat. And we know that the earth has a curvature. So several hundred kilometers cannot be taken as an approximately flat land, because we know for sure that there is a curvature, and that is why we have to look at the larger picture. And that's exactly what Newton did. So just like Newton, today let us look at the larger picture. So this is how approximately the earth looks like. It's a sphere, and this approximation is more than enough for our study right now. Now imagine there is a device which is capable of firing a ball with extremely high velocities, as we had spoken about. Remember, we need a horizontal velocity, a horizontal ejection, which is capable of taking the object hundreds of kilometers, if not thousands of kilometers, because that is where something interesting happens. Now imagine you gave a velocity to this particular object, a cannonball here, and you fired it horizontally. Now, if there were no gravity, if Earth did not have any capacity to attract it, the moment you fire this should have gone in a straight line forever. But that is not what happens. And that is not what happened with the football also, which you kicked from the top of the building, right? The moment you give a horizontal speed to this is going to travel a certain distance and fall to the earth. Remember, see this particular distance could be a few thousand kilometers, right? Now I want you to imagine in your mind that you have given much more velocity to this right now than what you did previously. Then what would happen? If you had given a slightly higher velocity to this, instead of falling here, it would still travel a further distance and fall here, right? Because it's a very simple imagination. You give more velocity, it should travel more kilometers before it falls to the surface of the earth. Now keep doing this in your mind. Still eject it with a higher velocity. Now it would fall somewhere here, let us say. It would be something like 15 to 20,000 kilometers. Now imagine you give further more velocity. Now let us say it traveled all the way up to here, right? Now imagine that you gave a certain speed to this, which was so high enough that the moment it got ejected, it is trying to fall to the earth at some point, but instead of falling, it just misses the earth and it comes back to the same point where it started from. Now what would happen? Now this is in some sort of a locked system with the earth, because you see it is trying to fall, but its speed is so high and its speed is so sufficient that it can miss the earth, and once it does that, it is capable of doing that again and again and again, and this would keep revolving around the earth instead of falling to the earth. But remember, it is the same gravitational force which is making it revolve around this. And this particular thought experiment struck a eureka moment in Newton's mind, because Newton knew very well that there is an object which does precisely that. It is our moon, and this moon is revolving around the earth. Everyone knew at that time, but Newton now knew that it is trying to fall to the earth, but it is missing it in a way, and that is why this moon keeps revolving around the earth, not because somebody has put it in that order, but because of gravitational force. Moon wants to fall to the earth, if I may put it that way, but it doesn't fall because every time it misses it. And this is where Newton understood that the same force which is making the apple fall from the tree, that same force is making the moon revolve around the earth. So as Newton was a physicist, he was a great mathematician even, so he decided to run a very few interesting calculations, and those calculations immediately gave him some wonderful insights, and what that insight led to is exactly what gave us today the universal law of gravitation. So we will do that. So let's look at that picture. As Newton was the master of mechanics, laws of motion, he knew very well that if an object has to revolve around a point, right? If an object has to revolve around a point, with uniform speed, there must be a centripetal acceleration. Centripetal acceleration. And centripetal acceleration, let me call it as AC, is given by an expression v square by r. Now, v is nothing but the speed with which this is revolving. An object is revolving around a point with the speed v, and that speed is v. And r is nothing but the radius, the orbital radius. So if you know with what speed it revolves around this point, and if you know at what distance it revolves, you can find out the centripetal acceleration. And centripetal acceleration, I'll get slightly technical, it's a vector quantity. It points towards the center of revolution. Now, Newton knew with little bit of data, he can find out the centripetal acceleration of the moon, because moon is doing precisely what this object is doing. This object is revolving around a point, and this moon is revolving around the earth, and that point could be center of the earth. So if this moon revolves around the center of the earth, I can calculate its centripetal acceleration. And what do I want to know for it? I want to know with what speed the moon is revolving and at what distance is the moon from the center of the earth. So from the center of the earth to the place where moon is located is called the orbital radius of the moon, and that distance is Rm. And with that knowledge, and if he can figure out with what speed it is moving around the earth, he can calculate the centripetal acceleration of the moon. Now, why he wanted to calculate the centripetal acceleration, you will come to know very shortly. So first we will do it, and then let us see what it will lead us into. So we will start. Okay, so if this is the expression for centripetal acceleration, let us see what Newton knew at his time. The distance from the center of the earth to the moon is roughly 384,000 kilometers. Now, was it known to Newton? Yes. But that might be surprising for you. How did they know it? Well, that's a different topic altogether. There is a lot of geometry involved, and there is a lot of trigonometry involved. And not just Newton, even many people before Newton, for even thousands of years, the Greeks knew all these data. So as I said, we will keep that topic aside. But what Newton knew was, from the center to the distance where the moon is located, and that distance is roughly 384,000 kilometers. Of course, units I'm talking in today's terms, which I can write it roughly as 3.8 into 10 power 8 meters. So this quantity, we have it. Now, they also knew the radius of the earth at that time, which approximately is 6,400 kilometers, or 6.4 into 10 raised to 6 meters. Now you might ask why this is required right now. Yes, right now I don't require this, but I'll need it very shortly. So just remember this. Coming back here, you can see the question arises. To calculate the centripetal acceleration, I need to know what is the speed of the moon. With what speed the moon is revolving around the earth. Now, that's quite easy to calculate if you know this, because we know for one full circle, right, again geometry, the distance traveled would be 2 pi times the radius. So this 2 pi rm would be the total distance traveled by the moon when it finishes one full revolution around the earth. And do I know what is the time taken for that one full revolution? Because distance traveled by time can give me the speed, an average speed, which is uniform speed in this case. So moon takes approximately 1 month. Newton knew it very well. Approximately it takes around 27.3 days to revolve around the earth. In today's value, I can write it as time period of the moon is roughly 27.3 days. And I can write it in seconds in SI units, which we use today, roughly 2.36 into 10 power 6 seconds. So there we have it. We have all the data required now. We know Rm, we know the time period, we will know V. If we substitute this in this expression, we are going to get the value of centripetal acceleration. And when you substitute these values here, he got the centripetal acceleration of the moon as 0.0026 meters per second square. Now, that's a magical figure for us, because this is going to lead into a path breaking thing, and that's precisely what Newton did. So, what did this number reveal? What did this whole exercise of finding out the centripetal acceleration, what did it give us? How is that related to the universal law of gravitation? That's the last part. So, we will see that now. Now, if you remember the first part of this talk, we knew Galileo and others had already figured out that all the objects, irrespective of their masses, when you are near the surface of the earth, they all fall with the same acceleration, which is 9.8 meters per second square, right? Now, observe this picture here. It's a complete picture. It's not up to scale, of course, but still it works for us. From the center of the earth till the surface, that surface is where all these activities happen, which we see in our day-to-day lives. And what do we see? We see all objects fall down towards the earth with an acceleration of 9.8 meters per second square. Now, as you go far away, that acceleration tends to change, it reduces. And if you see what happens to the moon here, it has an acceleration which is again pointed towards the earth, but there is a dramatic reduction. It is 0.0026 meters per second square. And of course, the acceleration is still pointed towards the earth, but only thing is we call it centripetal acceleration because of the reasons which I told you. Moon is revolving around the earth instead of falling to the earth, but acceleration is still pointed towards the earth. So, if you are near the surface of the earth, acceleration, what that force gives you is 9.8, and as you move far away, for the moon, for example, the acceleration turns out to be 0.0026 meters per second square. Now, how much of a reduction is that? If you calculate and check 9.8 over 0.0026 would give you an answer of roughly 3600. I'll call it as an approximation, 3600. Now, this is a very interesting number. Why? Why is 3600? Why is this ratio turning out to be an interesting number? This is where Newton's observation comes into picture. The distance from the center of the earth to where all these activities is happening is nothing but you can approximate it to be the radius of the earth itself, RE. And remember, RE was 6,400 kilometers. We knew this number, right? Now, this distance where moon is located from the center of the earth is Rm, and that was approximately 3.8 into 10 raised to 8 meters. Of course, you can write this also in meters, but this is the radius of the earth, this is the orbital distance of the moon, and this is the ratio of their accelerations. Looks a bit confusing, but let us try to make sense out of it. What exactly are we trying to do? If you take this ratio Rm by Re, this is roughly going to be 60. So remember, this distance ratio is turning out to be 60, this versus this, whereas acceleration ratio is turning out to be 3600. this is the final and the most interesting part. If you square this, Rm by Re square, this is going to be 3600 again. And this is not a coincidence. And this is what Newton knew. What exactly is the relation between this 3600 and this 3600? What is this telling us? Acceleration near the surface of the earth to centripetal acceleration of the moon is same as the ratio of Rm by Re whole square. Now this was a lot of information for Newton. Why? Because you see, acceleration reduces as inverse square. Near the surface of the earth, acceleration is g. Near the moon's position, acceleration is ac, which is 0.0026. And he knew that acceleration is reducing as inverse square. And he understood that this particular force which is making the apple fall down and which is acting on the moon, which is making the moon revolve around the earth, it is reducing as the square of the distance as you go far away. So that was a significant step. So what next? So the first part of the talk, Newton figured out, as I said, that all the particles, all the objects, whether it is apple or a heavier object or a smaller object, they all have the same acceleration, and that gave him an insight that force between earth and these objects is proportional to the mass of these objects, correct? Whereas this whole exercise of finding out the centripetal acceleration of the moon and comparing that with the acceleration near the surface of the earth, he got to know that that force has an inverse square relation. So combining all the ideas from his experience and his calculations and his insights, he came up with what we now call as the universal law of gravitation. And Newton's genius is he extended this to all the objects in the universe, not just for earth and apple, not just for earth and heavier object, not just for earth and moon. He said any two objects in the universe, any two particles in the universe, if they have masses m1 and m2, there is a force of attraction between them, and that is gravitational force. And that force is proportional to the masses of the objects. It is directly proportional to the mass. If the masses are heavier, force is higher, and it is inversely proportional to the square of the distance between them. Square of the distance between them. Of course, it should be from center to center, but still, let us approximate it. Force of gravitation between any two objects, whether it is earth and apple, whether it is earth and moon, or moon and apple, or apple and this object, or anything else. Any two objects in this universe attract each other with a force which is directly proportional to the product of the masses and inversely proportional to square of the distance between them. This is what we now call as Newton's universal law of gravitation. And later, this constant of proportionality was measured by Henry Cavendish, and we write the equation in the final form as F is equal to G m1 m2 by R square, which you have seen in most of the books. And G is approximately 6.67 10 raised to minus 11. Well, this constant and finding the constant is, as again I say, it's a different story altogether. How did he find it? But we know gravitational constant has been measured, and it is known as the universal gravitational constant. And here we have the universal law of gravitation attributed to Sir Isaac Newton.